Hi, this is Dr. Habib Ahmed, and today we are going to learn how to perform the Silvaco TCAD simulation of a bipolar junction transistor. I'm going to demonstrate how to create an NPN bipolar junction transistor and how to perform its characterization in the Atlas tool of Silvaco TCAD. I will show the Silvaco TCAD simulation of the NPN bipolar junction transistor Gamal plots, which are collector current and base current versus the base bias. Then I will demonstrate the collector current versus collector bias simulation of the transistor, and finally I will show the collector to emitter breakdown characterization of the bipolar junction transistor. So for this purpose I have created two codes, one code for the simulation of the Gamal plots and collector current versus collector bias, and the second code which actually demonstrates the collector to emitter breakdown performance of the transistor, which are IC versus VCE curves. Before running the simulation, let me give you a brief introduction into the topic of bipolar junction transistor. Specifically, we are going to talk about NPN bipolar junction transistor, which is one of the most common types of bipolar junction transistors, characterized by its three layers of semiconductor material. The three layers, or we can call them regions, are the emitter region, the base region, and the collector region. Then we got two junctions, the base to emitter junction and the base to collector junction, and we can see the depletion regions across these junctions as well. Let us talk about each individual region first. So starting with the emitter region. The emitter region in a bipolar junction transistor is heavily doped with donor atoms in an NPN transistor. Typically, the doping concentrations in the emitter region are in the range of 10 to the power of 18 to 10 to the power of 20 per centimeter cube. This high doping concentration ensures that the emitter has a large number of majority charge carriers, which are electrons in this case, available for injection into the base region. Now let us talk about the base region. The base is lightly doped with acceptor atoms in an NPN transistor. Typically, the doping concentration of the base region is in the range of 10 to the power of 15 to 10 to the power of 17 per centimeter cube. The base region is intentionally kept thin and lightly doped to minimize recombination of the charge carriers and in order to facilitate the transistor's amplification function. Finally, let us talk about the collector region. The collector is a moderately doped region with donor atoms in an NPN transistor. Typically, the electron concentration or the donor doping concentration of the collector region is in the range of 10 to the power of 16 to 10 to the power of 18 per centimeter cube. The function of the collector is that it collects the majority carriers, which in this case are electrons, emitted from the emitter. The moderate doping levels in the collector helps in efficiently collecting these electrons which are emitted from the emitter without significant recombination losses. When a small current flows into the base of the transistor, it controls a larger current flowing from the emitter to the collector. The emitter base junction is forward biased, typically around 0.7 volts for silicon based bipolar junction transistor, while the collector base junction is reverse biased. NPN bipolar junction transistors are commonly used in amplification circuits, switching circuits, oscillators, and logic circuits. They are fundamental components in modern electronic devices due to their ability to amplify signals and act as efficient switches as well. So the motivation of understanding the structure of an NPN bipolar transistor is that it is crucial for designing and analyzing circuits where transistors are used to control the current flow and for amplification of the signals. So with that preliminary information, let us now turn our focus to the code part. So the first code is about Gamal plots and plotting IC versus VCE characteristic curves for the bipolar junction transistor. We start with Go Atlas, which means that we are going to run the simulation in the Atlas tool of Silvaco TCAD. We define meshing. Here is the, okay, I have not plotted the structure, so let me plot the structure so that we can compare the meshing and the regions. Okay, here is the structure, and this is a previously simulated structure of another code, so I'm going to turn that, or you can say I'm going to close that. Okay, here is the code and the structure side by side for a better understanding and comparison. So we start with meshing. My structure runs from 0 to 2 micrometers in the x direction, as you can see in the structure as well, and from 0 to 1 micrometers in the y direction. Then I have defined meshing, like denser meshing for regions which are more crucial, especially the interfaces, etc., and sparser meshing where the regions are less significant from simulation point of view. After that, I have defined region number 1, and my material is silicon, so basically I initiated this structure with the silicon. Then I defined the electrodes for this structure. The emitter runs from 0 to 0.8 micrometers in the x direction. So in order to look at the electrodes, I'm going to right click on the structure, click on display, and then click on this icon, hit apply, and then click OK. So here is my emitter region running from 0 to 0.8 micrometers in the x direction. Then my base electrode runs from 1.5 to 2 micrometers. As you can see, here is the base electrode running from 1.5 to 2 micrometers in this structure. Then I have assigned collector electrode to the substrate, as you can see over here. Here is my collector. Then I introduce a doping of 5 into 10 to the power of 15 n-type initially for this structure. So instead of simulating the entire structure, let us simulate the structure step by step initially so that we can understand the doping part. The doping part is crucial, like how do we introduce the doping in the emitter region and in the base region and in the collector region. So for that purpose, I'm going to save the structure. So let me save it with my name, and then Tony plot, and then quit the program over here so that we can run the simulation step by step. So I run the simulation at this point. Here is my structure. We can look at the electrodes, and more importantly, I want to look at the doping levels. So I right click on the structure, click on display, then click on contours, go to define contours, and over here I click on net doping. So if you look at the color chart, my doping level is 5 10 to the power 15 per centimeter cube N type. Or to know for sure, you can go to tools, cut lines, draw a cut line across the structure, and here you can see that my doping level is 5 into 10 to the power 15 per centimeter cube. So initially we introduce electron concentration level of 5 10 to the power 15 per centimeter cube into this structure. Then let us move on to the next step. So now I'm going to cut this part of the code, which is the plotting part, and I'm gonna move it to next to the subsequent step. So then we introduce a Gaussian doping peaked at 1 micrometer along the y direction with a concentration level of 110 to the power 18 per centimeter cube N type. So looking at the structure, here is my 1 micrometer point. So basically we introduce a doping level of, or you can say N type doping level of 10 to the power of 18 per centimeter cube. Its peak concentration is going to be here at this point with a Gaussian distribution. So let us simulate this structure once again. Then we right click on the structure, go to display, contours, and we click on net doping, hit apply. So as you can see now, now the doping level is 10 to the power of 18 per centimeter cube N type. Or to know for sure, you can draw a cut line across the entire structure, and as you can see that the doping level at the surface is 5 10 to the power 15 per centimeter cube, and at the bottom of the structure it's 10 to the power 18 per centimeter cube. And by the way, if I right click on the structure and go to display, then click on electrodes, hit apply. So I have defined this part of the structure as collector. So what I have done over here is that since I'm working on NPN transistor, so the first thing I did is I introduced the collector part. It has an N-type doping with a carrier concentration, electron concentration of 10 to the power of 18 per centimeter cube. And step by step we are going to introduce the doping levels for the base region and also for the emitter region. So now let us move forward to the next step of doping. Here it is, and I'm going to run the simulation once again. Okay, so I right click once again, go to contours, and I display net doping on the structure. So here is my net doping level. So in the next step, what I have done is I introduce a Gaussian doping with a carrier concentration, or you can say p-type doping, at 1 into 10 to the power of 18 per centimeter cube, and with its peak at 0.05 micrometer, or you can say 50 nanometers. So as you can see inside the structure, we have a p-type doping represented by the purple region, and its whole concentration is 1 into 10 to the power of 18 per centimeter cube. And I'm going to tell you the purpose of this region after a couple of subsequent steps. Let us move to the next step. So I'm going to run the simulation once again. Here is my structure. I go to display, contours, and I display the net doping once again. Okay. So in this step, I am introducing a Gaussian N-type doping with a peak carrier concentration of 5 into 10 to the power of 19 per centimeter cube, and its peak is located in the y direction at 0. As you can see over here, this is an N-type region with an peak electron concentration of 5 into 10 to the power of 19 per centimeter cube. We can draw a cut line to know for sure about the doping levels. So as you can see, here is the doping level of this region, and basically this is my emitter region. So far I have introduced my collector region, and I have introduced my emitter region as well. Now I'm going to introduce my base region. We already have this region, but its doping level is slightly low. In order to make good contact over here to this, we have to introduce slightly higher doping level over here, close to the base contact. And for this purpose, we are going to move to the next step. In this step, I have introduced a p-type doping concentration peaked at 0 micrometers, and its peak carrier concentration is 5 × 10⁻⁹ per centimeter cube. By the way, in the previous step, I introduced the N-type doping of the emitter to the left of 0.8 micrometers. As you can see over here, I've introduced this N-type doping for the emitter to the left of 0.8 micrometers. Now in this final step of doping, I'm introducing a Gaussian doping to the right of 1.5 micrometers, peaked at 0 micrometers in the y direction, at a peak concentration of 5 × 10⁻⁹ per centimeter cube. So we go to display contours, we click on net doping, we hit apply. So now we see we have peak concentration over here at the base contact. We can draw a cut line over here as well. So you can see the peak carrier concentration 5 × 10⁻⁹ per centimeter cube. Okay, so what we have done so far is that we have created an N-type emitter region, and then a P-type base region, and then an N-type collector region. But we know that in an NPN transistor, the emitter is connected to the base region, and the base is connected to the collector region. So it means that we have to connect the emitter to the base region, but we have to isolate it from the collector region. So that's why you see over here that the emitter is connected to the base region, but we have separated it, or you can say isolated the emitter region from the collector region by this thin layer of p-type doping over here. If this was n-type doped, then the emitter would have been shorted to the collector region. So that's the purpose of the initial of this p-type doping introduced over here in this step. Okay, now that the doping is clear, we can move forward, and I'm going to run you through the rest of the code. Okay. So far we have created the entire structure of the bipolar junction transistor. Let me close this one. Then we introduced different models: OJ, Shockley-Red-Hall recombination, concentration dependent mobility, field dependent mobility, band gap narrowing, etc. Then over here I save the structure and Tony plot the structure. I'm using Newton method for the numerical simulation of my bipolar junction transistor. Then I ramp up the collector voltage from 0.025 volts to 2 volts, followed by ramping up the base voltage from up to 0.2 volts. Over here in this block of code, I actually want to look at the Gummel plots, which means that I want to plot the base current and collector current versus the base bias. So I have created a log file, and then I'm running a sweep for the base voltage from 0.3 volts to 1 volt, and then I plot this log file. So this block of code is going to plot the Gummel curves. Then I want to look at the collector current versus collector voltage characteristic curves. So for that purpose, initially I ramp up the base voltage to 0.7 volts, and then I have set the base contact to current control. So with this command we can actually set a contact to current control. If you don't do that, then your contact is set to voltage control. So I set the base contact to current control. Then I want to look at the IC versus VCE characteristics of the bipolar junction transistor at 5 different base currents: 1 microamps, 2 microamps, 3 microamps, 4 microamps, and 5 microamps. So at each of these base currents, I'm actually saving the structure, and then over here I've defined blocks of codes at each of the base currents. Here I load this structure which has a base current of 1 microamp. Then I create a log file and I run a sweep for the collector voltage initially from 0 to 0.5 volts with a smaller step of 0.1 volt, and then from 0.5 to 5 volts at a larger step of 0.25, and then I enter the command of logoff so that these log files don't interfere with each other. So I'm doing the same for 2 microamps current, and then for 3 microamps, and then for 4 microamps, and finally for 5 microamps base current. And finally I plot these curves onto the same figure using the overlay command in Silvaco TCAD, and finally I create the program. So now let me run the simulation. Here is the structure. We already looked at different parts of the structure, like for example, if once again we click on display, we go to contours, we can click on net doping, and this gives me the doping profiles of this structure. And similarly we can look at the contacts as well. So here is my emitter region, here is my base region, and here is the collector region. Here is the Gummel plot. So we want to look at the base current and collector current versus the base bias, or we can even include the emitter current. here are the emitter and collector and base currents. As you know that the emitter and collector current are almost the same for this kind of for the NPN configuration. So a bipolar junction transistor configuration, as you can see over here, the emitter current is slightly higher, but there is not a big difference between the emitter current and the collector current. However, the base current is much smaller as compared to the emitter and collector current. So these are the gamma plots. Then here are the collector current versus collector voltage. So I go to display, and here I choose collector voltage as the independent variable, and I want to look at the log plots, are in fact linear curves. Okay, cool. So here are the collector current versus the collector voltage characteristics of the bipolar junction transistor at different base current levels, increasing from 1 microamps to 2 microamps to 3 microamps to 4 microamps to 5 microamps. Finally, I want to show you the collector to emitter breakdown voltage characteristics of the bipolar junction transistor. And as I already told you in the start of the lecture, that I have created another code for that. Here is the code. We open the code. So the structure is the same. So I'm not going to focus on the meshing part and on the structure part. The structure is the same. We define some material parameters, the electron and holes recombination lifetimes for the silicon material. Then over here I introduce different models. For example, bipolar. The bipolar statement is set to specify that the default set of bipolar models is to be used inside this code. Now, the default set of bipolar models include concentration dependent mobility, field dependent mobility, band gap narrowing, concentration dependent lifetimes, and OJ recombination. So the purpose of this simulation is to show the collector to emitter breakdown voltage with the base open. Collector to emitter breakdown voltage is the maximum collector to emitter voltage that can be applied to a bipolar junction transistor in the reverse direction with the base open or not conducting, without causing a breakdown of the junctions. It indicates the voltage at which the transistor may begin to conduct significantly high in reverse direction, potentially leading to damage if the voltage exceeds that limit. Therefore, collector to emitter breakdown voltage is a critical specification that engineers consider when designing circuits using bipolar junction transistors, ensuring that the transistor operates within safe voltage limits and it can withstand potential reverse bias conditions without damage. Now, so then how do we introduce the breakdown model for this structure? So we do that using Silvaco model of impact ionization. The impact statement is used to specify the Silvaco impact ionization model required for the breakdown analysis of this code. Then here I'm introducing the Newton method for the numerical simulation of the structure. I ramp up the base voltage from 0 to 0.2 volts. I set the base contact to current controlled, and I have set the base current to 3 into 10 to the power of minus 15 amps. So as I already told you that we perform the simulation for the collector to emitter breakdown voltage by keeping the base open or not conducting. So to set the open base contact, it is necessary to define zero current passing through the base electrode, and this is done by setting the boundary conditions on the base using contact name base current, as you can see over here. Then throughout the breakdown simulation, IB is held at an extremely low value. So instead of zero value, I'm actually using an extremely low value of 3 × 10⁻⁻15 amps. And this is the most effective approach for performing the simulation of the collector to emitter breakdown performance of this bipolar junction transistor. Then I create a log file and I run a sweep for the collector from 0 to 10 volts at a step of 0.25 volts. And finally, I plot the IV characteristics of this bipolar junction transistor in order to look at the breakdown characteristics. So let me run the simulation. So I right click on the structure, go to display, and we are interested in looking at collector current versus collector voltage characteristics of this bipolar junction transistor. It's a semi-logarithmic scale plot. On the x-axis, our collector voltage is running from 0 to 10 volts. And on the y-axis we have the collector current, and as you can see over here that around you can say 8.5 volts the collector current starts drastically increasing, which means that we are arriving at the breakdown point of the transistor. So in order to operate the transistor in safe voltage limits, we should pretty much keep the collector voltage below 8 volts for safe operation of the transistor. So the collector to emitter voltage should be pretty much in the range below 8 volts for this structure. So that concludes the simulation session for today. Take care, and I will talk to you next time. Adios.